going from R theta to xy, and now we have xy going to r and theta. All right, so I guess that people will probably not notice the difference, but if you really think about what's going on, you will know that it kind of matters, because these tells you that what you're trying to do with those formulas. For example, these two problems, right? They were equations written in x and y. For some reason, they wanted to write them in terms of r and theta. Which equations should you use, right? So remember that you have things in x and y, but you want to have things in terms of r and theta, right? So you are going from xy into r and theta, and you see that this is what you did, right? But do you realize how complicated these guys are, right? I mean, if you say that, what's the point of doing it? Well, as you will see in a few minutes, that things are sometimes better with r and theta, right? But in this case, all you have to do is make substitution. But I guess that sometimes people will hesitate when they're seeing something that they knew what to do, but they just never actually do it, right? Most likely it will be like expanding expressions, like doing the perfect square trinomials. That's the formula that we use pretty intensively in the past couple of weeks. Now let's take a look at these guys. So first off, see that there's no x and y anymore. There's a whole bunch of r and theta. So it's very hard for a lot of our students, especially they have learned it, the trig or these things for the first time, right? Just to imagine what those graphs look like. It's just hard, right, in terms of r and theta. And therefore, like I said, if you like to convert radians to degrees to have a better idea what kind of angles you're dealing with, you could think about changing those equations from r and theta into the versions of x and y, so you can tell right away what those graphs are. But sometimes, oh yeah, go ahead, Russell. All right. But maybe some of them are not as bad as you thought. Say letter A. So r equal to 4 means that whatever points you're going to plot, and later you're going to connect them, to form a graph, they're all going to have the same exact distance away from the pole, right? Because r is the distance from the point to the pole. All those points are equal distance to the pole. When you connect all those points, what's the shape of the graph? A circle with radius 4, and they literally call it r. So that means r equal to 4 is a circle which is centered at the origin, which is the pole, by the way, right? It's the same thing. With a radius of 4. Can you guys imagine what the equation will look like for a circle with a radius 4 in the rectangular coordinate system? What does it look like? Circle with a radius 4, and the center is 0, 0. What does it look like using x and y? So back in college algebra, right? Think about it. Just imagine what it looks like. I'm sure that right, what it is. And you will see once we've done the conversion from r and theta to x and y for letter A, it should be exactly what you expected. Well, let's do that. But now you have to think, like, what do I do to get rid of the r? And I need to get x and y. Then you come over here and you see that, oh, I see an equation that has r, which is already isolated, right? It tells me that it better be something about x squared and y squared. Isn't that what I can do? Just go ahead and substitute right? The radical x squared plus y squared for the r on the left hand side of the equation, and that's pretty much it, right? Let's say r equal to 4, but instead of doing r equal to 4, I will substitute square root of x squared plus y squared for the r. You still set that equal to 4, right? And technically speaking, you're done. But no one's going to leave that, equation with the radical, because you could have just squared both sides to get x squared plus y squared equals 4 squared. Now, again, if you have thought about the equation for a circle center at the origin with a radius of 4 in terms of x and y, is this the form you're looking at? It should be, right? But which one is algebraically simpler? This has to be it, right? Hard to imagine, but you have to admit that algebraically a lot simpler. So polar coordinates do have their own benefit. Otherwise, why do you think that mathematician came up with that? Let's take a look at letter B. You have an angle theta, which is 3 pi over 4. And by the way, so please, nothing wrong with you converting radians into degrees. And it turns out that this is 135 degrees. You have an angle, right, which is given. And it's not a bad angle. You can always calculate it, and you'll see that it's a kind of nice number. But now I need to get rid of the angle theta, right, in a way so I can get x and y. So again, you go through those equations, and you realize that maybe this is the one we can use, right? This has pretty much just the theta by itself. We just have to take the tangent of it. But we know what angle theta is, right? It's just 3 pi over 4. So what if I take tangent theta, which is, tangent 3 pi over 4? And that has to be y over x, right? See that? This is the formula we have, right? That bridge the theta and x and y. It's just that we realize theta has to be 3 pi over 4. I substitute in. And now, what would you do if you see something like that in a test? I don't care whether it's going to be a question or somewhere, in a problem, right? They told you tangent, 3 pi over 4. Would you go ahead and calculate whatever, right away to see how much it is? And you could do that, right? Because you don't have to memorize, this kind of angle. But make sure that you're in degree mode, radian mode, 3 pi over 4. I believe that if you do that, in the calculator, it will return -1. Okay, so evaluate this guy, tangent 3 pi over 4 is -1. That's on the left-hand side, right? And again, technically speaking, you're done. But again, people will prefer that you get rid of the denominator and write that equation in a much nicer form. So would you say that's going to be y equals -x? So now what about the graph of it? What does it look like? Equation as simple as y equal to -x. First off, the shape has to be a straight line, right? Okay, is it going from the second to the fourth quadrant, right? Yes. And you know what? This is called slope-intercept form, right? With that -1 to be the slope. But so now, if you come back to this, does it make sense that theta equals 3 pi over 4 for all the points that line up on this line? So now I guess that if you remember how we plot those points, and also remind yourself that since they didn't mention anything about r, that means r could be anything. All those points could be as far, as close to the pole as you want, but they all going to have the same exact angle that makes, from the positive x, right, in the counterclockwise direction, sweeping out an angle of 135 degrees or 3 pi over 4. That means they all have to line up, right, in a line like this. And the angle is 3 pi over 4, right? So again, not too bad. Now, what's bothering people based on, my first year students, they're not happy about letter C. So let's see how that works out for you guys. So C says we have R equals -2 secant theta. So, I mean, now what do we do? So we don't want to have R in a theta. And we know that R and theta are, depending on X and Y, right? I mean, I can replace the R, right, with, let's say, radical X squared plus Y squared, right? But what I'm going to do with the secant theta. But I do have tangent theta, right? So if somehow I can cook up the right-hand side to make it look like a tangent theta, then I would be able to replace that with y over x. Please say, I'm getting rid of the theta. But is it possible to turn the secant theta into tangent theta? You're going to have to pay some price, right? But I'm saying that, is it possible? So now, how do we do that? Okay. You could. So now if you have R times R, it will be R squared. That's nice, right? R squared is X squared plus Y squared. But what is R times secant theta? Now, it would be better if it has R times cosine or sine theta. Well, then the cosine is going to be in the wrong place, right? So, but that's a very good trick, that you definitely want to try, right? So you see that in letter D. But again, thinking about my question, is there any identity? Also you're shaking your head because you don't want to think of, well, because when I say identity at this point, so maybe I remind you the chapter 6, right, the tunnel dome. But if you calm down and think about, was there an identity that relates the tangent theta to the secant theta, right? And okay, Malaka, you know that? Yes, right? Now, see that? So, technically speaking, if all we care is you guys know those identities after pushing you guys in a kind of a harsh way, right? Taking a test. So now, I mean, you guys probably didn't still remember all the identities, but you remember most of them. Not to mention the one that wasn't really that popular, right? You guys all know sine squared plus cosine squared equal to 1, but now you know the other version, right? So now let's take a look. So we have, let me put that as a side note. So we have 1 plus tangent squared theta equals to secant squared theta. And I know that I like tangent square better than the secant square, but how would I get rid of the secant if it's not even squared? If it was squared, then I would just, substitute right away. Power, reduce the power. It will only work if it's cosine square or sine square. Guys, you're looking at an equation. You want something on one side of the equation to be squared. What would you do? Square both sides, right? So let's do that. So we'll square the R and also the -2 secant theta, right? So this will be R squared. Still not a bad thing, right? Because R squared is going to be X squared plus Y squared. So this is going to be 4 times secant squared theta, right? So now let's go ahead and make the substitution. R squared is 4 times secant squared is 1 plus tangent squared, right? 1 plus tangent squared theta. Okay. Now, what are you gonna do? You see that r, right? Square it, so you get x squared plus y squared. This is 4. 1 plus. Now, tangent theta. So again, let's remind ourselves. Tangent theta is y over x, which means that if you square it. Oh, Mateo, could you get the door for me? Thank you. Tangent squared will be y squared over x squared, right? Just squaring both sides. So now I'm looking at y squared over x squared. Oops. Oh. There's a square here. So once again, you're not wrong if you were to just leave it like that, because that's an equation they want, right? Instead of x and y. But it's not very conventional since you have denominators, right? And it turns out that it's going to be not nicer if you simplify it. So now here's the algebra question. How would you simplify this equation as much as you could? What do you want to do? Do you see that something that could have been removed? You could distribute it for it, yeah. You can either do it now or later. But I guess that the denominator should be kind of concerning, right? So now if you want to get rid of the denominator, right, multiply both sides with x squared, right? Just like the rational equation kind of thing. So let's do that. So I'll multiply the right-hand side with left-hand side with x squared, the right-hand side again with x squared. So again, I'm letting you know, all I did was multiply the same thing on both sides of the equation, right? And now I will distribute x squared. I'm going to do that on the left-hand side. You'll see why in a second. I'll distribute the x squared from the right-hand side. Don't do the 4. Leave it there. So x going to get into the parentheses. Hit the first term. You get x squared, right? When the x squared times the second term, you have y squared over x squared times x squared. So x squared cancel, left with y squared. Now what? You will divide out the x squared plus y squared, right? You arrived at x squared to 4, right? And what will you do next? X squared is, plus or minus 2, right? Okay. And this is why that, first year students not happy about kind of algebra, right? They kind of see like, it's somewhat doable, right? But not straightforward. But now, it's getting to a point that we need to be a little bit more innovative when it comes to making substitution, because this is not recommended. Okay, not to mention there's a little issue there. So now let's see if we can do the letter C in a smarter way. Hey, try this. So I'm looking at R equals -2 secant theta. Do you see that? We are looking at either tangent theta or sine and cosine, right? I mean, we should be better off with anything other than secant and cosecant. How about we turn the secant into something else? Maybe, yeah, the reciprocal of cosine, right? Let's do that. So I'll write it as R equals -2 over cosine theta, right? Using the reciprocal identity. Now, how about I get rid of the denominator, just like I did over there, right? So I'll multiply both sides by cosine theta. So R times cosine theta equals to -2 over cosine theta times cosine theta. And once again, I was just multiplying, same thing on both sides of the equation. And what you get on the left-hand side is r cosine theta, right? The right-hand side, cosine square cancel, left with the 2, -2. But what is r times cosine theta? Yes, x. So, oh yeah, Alex. Yeah, and we'll see why that we got 2, and we realize later in the right way or in a smarter way that x to the plus 2 is not, a valid solution. But I'm glad you noticed that r times cosine theta is -2. Okay, so now let's reflect on what we just did. But with the smart way. First off, you remember that, back in chapter 6, there was a tip in verifying identities, right? We say that, hey, you might be better off with sine and cosine. If it was not written in terms of sine and cosine, think about, rewriting it. So once you do that, I mean, do you see that in general, you wish that you don't have to deal with denominators? And we're blessed by the equation because we can easily get rid of the denominator. And once you do that, you realize there's some combination r and a cosine theta that happen to work out as x. But this might be harder than you thought because, again, if you're under pressure or if you've been looking at these two the whole time, would you still realize that you get something that's kind of nice that you could have just get x right away, right, without doing anything crazy? But that's the question, all right? So it might not always happen. But once you get the x equal to -2, you're done, right? So now let's get back to Alex's question. How come, or does it mean that x equal to +2 is not supposed to be there in the first place? And the answer is yes, right? So, but the problem is, if now we realize we're not supposed to have x equal to +2. Is there anything wrong we have done on the left that has led us to that wrong solution? Anything algebraically that's, not super wrong, but problematic, that end up including a possibility that's not supposed to be there in the first place. Okay, so let me find a color that's actually bad so that that's something wrong. You know what? I'll use that. Oh, that's awful. And you know what? Maybe it's still yellow. And I'll put a big question mark. Would there be any problem if you just simply square both sides of the equation? And first off, you probably don't do that all the time, so you probably won't realize there could be, some serious issues. Or since you're not looking at certain numbers, you might not see it right away, right? So let me show you an equation. So -2 equals -2. That's fine, right? So that's a valid equation. Am I allowed to square both sides? Yeah, right? -2 square better be the same as -2 square, which is 4. Go to 4. But now, let's say, somehow you decide not to tell your reader the whole story. You say, look, I have an equation, 4 to 4. It came from, there's no way to, okay. It came from squaring another equation. Would you be able to find out the equation before I square it? So like I said, I squared the equation, I got to 4 to 4, right? I'm asking you, what would be the equation before I square it? Would you know it was -2 equal to -2? Without me telling you that was the case? You'll say it's 4, it might be 2 equal to 2, right? What happened? Because that square pays no respect to the negative sign. That means you introduced ambiguity by squaring the equation. It's valid going one way, but not the other way around. People won't know what's going on. And this is actually what's happening. Over here, right? Do you see that? Now you can act that, you know what? I knew x has to be -2. Let's see what's going on with this particular student. By squaring that equation in the second line, he didn't realize x is supposed to be negative. And if x is negative, squaring it is going to be fine. But there's no way that the math is going to realize, right? And math includes both possibilities because you know what? If x is positive, everything works out still fine. But somehow, this is the only possibility. Anyway, so now, besides the side notes, there are two ways of doing it, right? The lengthy way, right? And the shorter way. I'm sure you see that this is way much better. But is that intuitive enough for you to do it all the time? I mean, it should be, right? If you're flexible with these equations, right? Because I say that the only thing that you might not be that used to is, would you recognize at this point that r cosine theta is x? If you do, you're done. If you don't, that you get stressed out, right? Because wait, why is that still complicated? And what is r times cosine theta, right? That's the only downside of it, right? Now let's try one more problem. Then I want you to be again flexible with all these many equations. If you are able to do that, then it'll be a lot easier for you to figure these out, in a test. Letter D, r equals 10 sine theta. R equals 10 sine theta. All right, so let's write it down. R equals 10 times sine theta. So what I want everyone to do is don't jump into the math. Stare at that equation for 10 seconds. And you want to tell me which of those 4 equations would be the best for you to use and how. Go ahead, stare at that equation. Pick the best one, not the one that might be ready, right? But the one that you think maybe, like 3 steps ahead of time, like you're playing chess, right? You're gonna think about, what if I do this? What's the other guy's gonna do, right? Picture yourself in the 3 steps in the future, and you find which of those might be the best one to use, and how you're gonna make it happen. Any thoughts? You guys thinking about this one? Oh, Alex, you have. Okay, r equal to y equal to r sine theta. And you do realize that r and sine theta are multiplying each other, but they're not in that equation. How would you make them get together? Okay, now remember that it's an equation. You can add, subtract, multiply, and divide the same thing. If you want r on the other side, why don't you multiply r on both sides? All right, so let's do that. R times r should be the same thing as r times 10 times sine theta, right? And all I did was to multiply r on both sides. So now you see that it's oh, you know what? What's that saying? One stone, two birds. Is that the right way to say it? Close enough, right? Because that's exactly what we say in Chinese, but we'll try to. But they have something like that. Do you see? We did two things at the same time, right? Just by multiplying r on both sides. Do you guys see that r squared? How nice it is, since you can easily turn that into x squared plus y squared. Not to mention, you got what you want because r sine theta is going to turn into y, right? So r squared equals 10 times r sine theta, and therefore this is x squared plus y squared, right? And this is 10 times y. Let's put it 10y. And technically speaking, you are done. And of course, if you want, you can take that negative 10, 10y to the left, right? But you don't have to. Okay. And also, you will see if you do move 10y to the left-hand side, it will be a circle. It'll be a circle with a shifted center. Okay. But I'll leave that to you to find it out. But now let's take a close look at both problems. And think about how do we actually take advantage of all four equations, right, in a more like a strategic manner. It's not like blindly follow, those formulas. You could, right, but you might get stuck somewhere. So if you could think, well, of course, the best way to do that is as you're trying those quiz problems or the homework problems, right? You might see that sometimes you do certain thing that you thought that's going to work out in general, but turns out that it's getting a lot more complicated, right? But if you hang in there, you might still work it out. But I'm telling you, like especially in letter C, right? Think about some general tips we had back in the chapter 6, and those tips like factoring out something. Oh yeah, Russell. Yeah. But you're saying that is there some other ways to deal with secant data? Is that what you're trying to say? Oh yeah, of course. There could be cosecant. It's possible, that not very likely, because it gets, you won't, it's even hard to imagine by adding like another function, right? Or the equation has not just secant, it has tangent in it, or it has secant and cosine, right? That just get a lot messier. All right. So that's everything in 7.3. So now you know that I don't get to be here on Friday to get you the quiz, right? But seriously, everyone should be able to figure it out, all the questions, right? Every single one in the quiz packet. Not to mention, if you take a look at number 19 to 21, I'm not going to discuss it, since people have to still come out and take it. Do you have any thoughts about 19? Writing that equation into x and y. Theta is 5/6. Then we just do this problem with a theta being a different angle, right? That's exactly the same problem, right? Did we do that as well? That was letter D, right? Instead of having cosine, it's sine theta. But 21 is a bit tricky, right? R squared, well, which is kind of nice, right? But what about sine 2 theta? If you know the answer, keep it to yourself. If you don't, all I have to say is remind yourself, what do you call it? Sine of 2 theta. Double angle. And I guess that, you know, it's probably not a good reason why you have to use it, but at least that you see you have identity, right, for it, and maybe that's exactly what they wanted to do, right? Now, since I do have a few more minutes, so I do want to get started with 7.6, which is about vector. I'm not gonna seriously like do a lecture kind of things. I'll just introduce some you know, background, or just introduce the concept of vector. So I hope that you guys will be open to some math that you might not be that used to, since you're just dealing with the numbers, or the traditional sense of numbers for so many years, and then, you know, it gets hard to get used to some kind of a new set of rules, right? Anyway, now just curious, do you guys know by any chance like what a vector is? Maybe from a prior class, like maybe geometry. They do mention vectors in geometry a little, or maybe algebra 2. No, I guess, you know, they should have, you know, vectors in pre-cal or even calculus. But the anyway, physics. By any chance that anyone have taken physics in your 9th, 10th grade? You did that a year, like a physics honors? Do they have? Well, they better have a lot of vectors. Okay, yeah. But I guess that you know, it's not very often that people are taking physics, you know, at maybe you know, 9th or 10th grade, right? Okay, don't worry. Now this is what I'm gonna do. So take a look at this equation. Does that look like a correct equation to you? No, right? That's not a bad equation in the arithmetic sense, or in the pure number sense, right? But what if I tell you that these 3, 4, 5 are not traditional numbers? They are numbers with directions. But can you imagine what kind of numbers in a real life situation that it has directions? Force, right? Or let's say for those who hasn't learned physics, just think about your daily life. Has there been any numbers that you always, you know, have to deal with that has not just numbers but also directions that kind of matter? Christopher? That's a speed, right? Or a velocity, yeah. Because, you know, if you're thinking about how fast you travel, don't you have to worry about, you know, in which way you're traveling, right? So if you're driving like crazy, you know, trying to get home, right? But instead of heading straight to your home, you went the other way around. I mean, you're still gonna get there because you go around the Earth and still get there, right? But so direction matters, right? Now, one of my first year students says that, oh, numbers with direction. Would it just be you walk, right? You know, 10 meters one way, right? Then you go the other way around, right? So maybe another 10 meters, right? So, you know, maybe movement. So now let me show you there is a way to make this equation still a valid equation, but not in a traditional sense. Say there's this guy who started to walk from point A to point B in the eastward direction, right? Straight to the east, and traveling 3 meters. And he's gonna go, oh shoot. And he's gonna go to, you know what, I guess that I should get a more distance. And he's gonna go straight to the north, walking 4 meters. Get to point C. Now, here's a valid question, right? How far you think it's going to be? How far do you think this guy's going to be away from the starting point? Walking to the east, 3 meters. Then to the north, 4 meters. How far do you think that this guy's going to be away from the beginning? 5, right? How would you figure out the 5? The Pythagorean theorem. So basically, you're looking at a right triangle. Come on, the curve. Right, that's the side AC. And if you work it out, that has to be 5 meters. But that's based on the fact that, since this is a right angle. Now, what does it mean? It means if he goes from A to B and from B to C, it's equivalent to this guy just walk straight ahead to the C, right? Because that's the same starting and the end point. So therefore, 3 plus 4 is 5 in a geometric sense, right? Or in a sense that the direction of the movement actually kind of matter. Yeah. For a triangle, yeah. The sum of these two sides must be greater than the third side. So now you're exactly looking at the point or the thing that bothers people. Because 3 plus 4 is greater than 5. That means you're better off to go straight ahead, not taking a detour. And you know that the shortest distance between 2 points is the straight line distance. And you know to make a triangle, these two sides has to add up to be bigger than the 3. Sorry, bigger than the 5, right? There's so many ways you can see that has to be true, right? That equation, 3 plus 4 is 5, is a valid equation under a certain condition. And I'm showing you this is one of the conditions, right? So now, just to make the equation a bit more properly written, so that you don't confuse people, we will put arrows on those numbers to let people know those are not numbers in a regular sense. They're numbers with directions, right? You see an arrow, right? And you know what? How do we call those numbers? They're called vectors. So do you see that vectors are numbers, pretty much numbers in a 2-dimensional sense? Because the direction matters, right? Well, guess what? You guys live in a 3 dimension. So it's not too much to ask you to think about things in the 2 dimension because it's just some things on the paper. But you know what? It's even worse. We live in 4 dimensions. 3 dimension space, X, Y, Z, 1 dimension in time. Right? And that's what's making things even harder for you to imagine. Right? Anyway, so but we'll see. Hopefully that. But what I can promise you is, in the section about vector, you will see some strange rules that you haven't never seen before. But when it comes to math, like if you want to calculate things, the things you need is basic trig. What I mean by basic trig is right angle trigs or SOHCAHTOA. Not to mention that if you do get angles greater than 90 degrees, you have the calculator, right? Not to mention you have the quadrant things, but I'll make sure that there's always going to be a way for you to just use the right angle trig to figure this out, right? Anyway, so that's all I want to do. I'm sorry, I'm keeping it a bit too long.